Okay, so we've been talking about the shapes of molecules, and one of the things that's important, and the reason we talk about shapes of molecules, is because it helps us to understand the properties of compounds. And one of those things is properties like miscibility. So if you look here, this is oil and water in a glass. And you probably know from personal experience that oil and water just do not mix. You can think of Italian salad dressing. You can shake that up and you set it down and the oil starts to go to the top, the vinegar part starts to go to the bottom. It just does not stay mixed together. Why is that? Why won't those things mix? It has to do with the different properties of the water molecules and the oil molecules. The water molecules bunch together in one region. They are very attracted to each other, and so they seek each other out and they clump together, and they exclude the oil molecules. So the oil molecules get pushed out. The reason the oil's on the top is because its density is less. Water does this with other substances that are more dense, and then that layer ends up on the bottom. The reason is that water molecules are especially attracted to each other. So when we look at this water molecule, it looks like it would be a linear molecule, but we learned from Vesper theory that because of these two lone pairs, it's actually going to be a bent molecule. But then there's something special also about these bonds. The hydrogen and the oxygen bond, it's a single bond, so it's a sharing of two electrons, one pair, but those electrons are not shared equally. Okay, that happens when people share things as well. If you've ever shared a bed with someone, you know that the blankets are not shared equally, right? There's always somebody who steals them and hogs the blankets. Well, that's the case with these electrons. Oxygen is the blanket hog. Oxygen takes more than its fair share of the electron pair. And that has big implications for properties of the molecule. Why does oxygen do that? Well, oxygen is more electronegative than hydrogen. Electronegativity is the ability of an element to attract electrons within a covalent bond. It is just, a property that we have observed. It's set on an arbitrary scale, a relative scale, and so fluorine is the most electronegative element, and so that's given an electronegativity of 4, and then it goes down from there. So electronegativity, the ability to attract electrons in a bond. So we could look at the oxygen-hydrogen bond as illustrated here. Here's oxygen, here's hydrogen. And these dots represent the pair of electrons. Where are they at any given point? So sort of like a multiple exposure photograph. And what we find out is that the electron pair spends more time over here than it does around the hydrogen. And the result of that is that the oxygen end of this bond is slightly negative. We use this delta, that's a lowercase Greek delta. Capital delta is a triangle. It means change in. And so this is a lowercase delta, it's a small change. So this is a partial negative charge and a partial positive charge. These are not ions, but they're kind of getting closer to ions. They're not sharing equally. So this is my chemistry land analogy for this. So the electrons are two little boys. Electrons are a lot like little boys, kind of squirrely and unpredictable. So here's the one house. One electron came from the oxygen home and one came from the hydrogen home. Now, these homes are not the same. At hydrogen's house, they have an old black and white TV and a VCR with some banged up Thomas the Tank Engine videos. They don't have a swimming pool. They don't have a play structure. If you're hungry, Mom will give you some bread and a cup of room temperature water. She won't even butter it for you. So over here at Oxygen's house, they have the big screen plasma TV. They have all the game systems. They've got a trampoline and a swimming pool in the backyard. They've got a soda fountain in the kitchen. If you're hungry, Mom has Pizza Hut on speed dial, right? So if you were this pair of little boys, whose house would you play at more? Oxygen's house. Why? They've got everything. It's more attractive, right? It's more fun. Oxygen is more attractive to the electron pair, so the electron pair spends more time over here in that bond than it does over here. Now, do those little boys ever go over to hydrogen's house? Sure, they do, but not very often. They spend most of their time at oxygen's house. They go over to hydrogen occasionally. Any questions? So this bond then has what we call a dipole moment. I've overlooked this part. A dipole moment. So if you think of the poles of the Earth, right? The North Pole and the South Pole. Those represent magnetic field differences. So a compass points to the North Pole because that's how the magnetic fields are. So the two poles of the Earth are different, right? We sometimes talk about polar opposites, right? At opposite poles, very, very different. So a dipole means that this bond has two poles, and one is negative and one is positive. And so there's a charge imbalance here, a separation of charge. A bond like that with a dipole is called a polar covalent bond. The electrons are being shared, but they're not shared equally. So one end is more negative than the other. That dipole moment has a magnitude, a size, and the size of that depends on the difference between the electronegativity in the two elements. Larger difference, more polar; smaller difference, less polar. So here is a graph representing the electronegativities of the elements. There might be an occasional question where you actually have to look at the numbers. What I want you to understand, though, is the trend in electronegativity. If you look at this, fluorine is the tallest here. Fluorine has the highest electronegativity. As you get closer to fluorine, electronegativity increases. It follows the same trend as ionization energy. So as you go across a period, electronegativity increases. As you go down a group, electronegativity tends to decrease. So pretty much if it's the closer to fluorine it is, the more electronegative. So if we have a bond like this one between two chlorine atoms, is there a difference in electronegativity between one chlorine atom and another chlorine atom? No, they're the same element. They have the same electronegativity. So then there's zero difference in electronegativity. Then those electrons are going to be shared equally, and there is no dipole moment. This is called a nonpolar bond. This bond does not have one end that is different from the other. It's nonpolar. And so the electrons are shared equally. Anytime you have two atoms of the same element, they are exactly the same, is going to be a nonpolar bond. Now, is it possible to have a nonpolar bond between two elements that are different? Yes, it is. If you look here, nitrogen has an electronegativity of 3, and chlorine has an electronegativity of 3. So a nitrogen-chlorine bond would also be nonpolar. So that can happen. Excuse me. If the difference is very large, kind of like what I described with the hydrogen and the oxygen, I exaggerated a bit there. If the electronegativity distance is very large, then the electron's completely transferred. So in chemistry land, this is like the home that's not as attractive. Maybe, dad beats the child, and there's abuse going on, and it's really a bad situation. And so the family next door actually adopts the child, right? So now he doesn't go over there really at all. He's adopted out, and he's going to live with this other family. That would be the equivalent of an ionic bond. So chlorine has the child permanently, and sodium does not. And so now we have actual full charges on these. They've become ions. And then they are attracted by the opposite charges. I haven't worked out what that equates to in this analogy yet. Sorry. This typically happens between a metal and a nonmetal. If there's an in-between, not extreme like a metal-nonmetal, but not identical like two of the same element, then we have a polar covalent bond. And these are common between two nonmetals. Here we've got hydrogen and fluorine. Fluorine is the most electronegative, hydrogen is not, and so this is a polar covalent bond. So like many things, there are not hard and fast divisions between these different types of bonds. It's sort of a sliding scale. The electronegativity difference can vary from 0 up to 3.3. That's the largest electronegativity difference. And so we kind of have to draw some lines in here and say, well, what do we consider polar? What do we consider ionic? And so we've chosen to draw the lines here at a difference of 0.4. If the difference is 0.4 or less, then it's considered a nonpolar bond or a pure covalent bond. Intermediate is in here. If you have a difference of 2.0 or more, then it's considered an ionic bond. So this is the truth here. I'm telling you the truth. But you don't actually have to remember this much detail. So now I'm going to tell you what I want you to remember. Okay? The book uses this term pure. I prefer nonpolar, a nonpolar covalent bond. And this is between the same elements. So you've got two chlorines. The one exception that I'd like you to remember is carbon and hydrogen. Carbon-hydrogen bonds have an electronegativity difference of 0.4, so they are considered nonpolar. They are very, very common in organic chemistry, and so that one is worth remembering. The polar covalent would be two nonmetals. There are some exceptions, but I won't get you with them on an exam. If you have two different elements and they're both nonmetal, I want you to say that's a polar covalent bond. And an ionic bond would be a metal-nonmetal. Okay? So these numbers, the differences are really nice. We're not going to do that on exams. I don't expect you to remember that. Two of the same element, or carbon and hydrogen, that's a nonpolar bond. Two different nonmetals, it's not always true, but it will be true on my exams. Two different nonmetals, assume that that's a polar covalent bond. Metal, nonmetal, ionic bond. Any questions? So, let's do this one. Is the bond formed between each pair of atoms pure covalent, polar covalent, or ionic? So iodine and iodine, what's that going to be? Nonpolar. Two of the same element, so that's nonpolar. How about cesium and bromine? Got to look at the periodic table. That's ionic. Cesium's a metal, bromine is a nonmetal. How about phosphorus and oxygen? Polar covalent. You got that? Sometimes more detail is required, but usually not. So let's not bother with the details. So we've learned to identify polar bonds. A molecule can have polar bonds, though, and still be nonpolar overall. So a polar molecule has a net dipole moment. the polar bonds add together instead of canceling each other out, and so we have a polar molecule. The molecule itself has one end that's more positive than another. If you have a diatomic molecule, diatomic means two atoms. So if there's only two atoms, there's only the one bond. If that's a polar bond, the molecule's polar. But when you have more than two atoms, it becomes a little more complicated. Let's look at carbon dioxide. So carbon dioxide's Lewis structure is here. We see that there are two electron groups, the two double bonds. Two groups get away from each other by going on opposite sides. And so this is a linear molecule. The geometry here becomes important in predicting whether the molecule is polar. Carbon and oxygen are two different nonmetals, and so the electronegativity difference is 1, but I would expect you to assume that that's a polar bond, and it is. So carbon and oxygen. Look at the periodic table. Which one is closer to fluorine? Oxygen, right? That means that oxygen is more attractive to the electrons. It's sort of like a neighborhood where fluorine is the coolest house, and it kind of moves out from there. So oxygen's more electronegative, and so this arrow is describing the atom that is more attractive. I think of this a little bit as being Dad's out mowing his lawn, and somebody comes over and asks, "Hey, where's Junior?" And he says, "He's over there," right? So that's the arrow pointing. He's pointing to where the two boys are playing. So he's pointing at the cool house. And then this positive sign here is indicating that this carbon has a partial positive charge. Now, because of the geometry of this molecule, we've got a dipole here with a negative end and a positive end, and we have a dipole over here that is the same strength, but in the opposite direction, and so these cancel out. If you're into math, this is vector addition. If you're not into math, let's think about playing tug-of-war. So here we've got a guy in the middle, and he's holding onto these ropes, and then we have guys over here pulling. If these guys on the outside are equally strong, and they're pulling exactly opposite of this guy, is he going to move at all? No. Now, maybe they'll pull his arms off, but, he's not going to move, right? So maybe that wasn't very good. Maybe we should think of this as being, this is the red flag. Oh, this is getting way too elaborate now. They sometimes put a red flag in the middle there to see who wins. So they're pulling in opposite directions. Does the red flag move if they're equally strong? No, it doesn't move. This is a nonpolar molecule, even though it has polar bonds. Do you have any questions about that? So we represent polar bonds with arrows or vectors that point in the direction of the negative pole, the plus sign, at the positive poles. If those point in exactly opposing directions, the dipole moments cancel out. What about water? Well, this one doesn't show the Lewis structure. Are those too big? No, those are good. Water has, maybe those are a little big. Water has two lone pairs, and so it's got 4 groups. 4 groups make a tetrahedron. 2 of those groups are invisible, and so water has a bent structure. We have this oxygen-hydrogen bond. So we have a polar bond because oxygen and hydrogen are not the same element. We look at the periodic table. Oxygen is closer to fluorine. It's more electronegative, and so that's why the arrows are pointing to oxygen. So now, if we think of this, and we're playing tug-of-war, and we're moving, we're pulling at this angle, is the red flag going to move? Yeah, it is. It's going to move this way. And so water has a net dipole moment. The molecule itself has a positive end and a negative end because the oxygen is hogging the electrons, and so this end of the molecule is going to be more negative, and these ends are going to be more positive. Actually, I drew that arrow the wrong direction, didn't I? I was thinking about the flag, and that's why I didn't do the flag anymore. Now I remember. So here we got this guy. Ooh, he's got long arms. Maybe he's a gorilla. And we got two little guys over here. This is better. So strong guy here, higher electronegativity, pulling against these weak little guys, less electronegativity. What direction is this guy going to move? He's going to go up, right? The net movement is up like that because he's going to pull them. He can pull both of them. So there's net movement. This has a dipole moment. It's a polar molecule. Any questions? So there's a bunch of different possibilities, and they're all based on the geometry of the molecule. If you have a linear molecule and the bonds are polar, it's still going to be nonpolar because they're in opposite directions, they're going to cancel out. If you have this trigonal planar structure where you have three bonds that are polar but they're all the same, that's also going to be nonpolar. Because you think about a guy here in the middle and somebody pulling this way, someone pulling that way, someone pulling this way, and they're equally strong. The guy in the middle is going to be really, stressed out, being pulled all over the place, but he's not going to move because the force is balanced. Here is like water molecule where these are going at angles and they're not going to cancel out. This one's going to be polar, that one's going to be nonpolar. So it would be great if all of you understood vector addition and could visualize this and see what's going on. This is what your book says the steps are. I'm going to tell you a shortcut in just a minute. Does the molecule have polar bonds? Figure out whether those bonds add together to form a net dipole moment. So you have to use Vesper theory to find the geometry and then decide if it's symmetrical. Here's my alternate method. This works most of the time, and that's pretty good, if you ask me. So this is what you do. You have to start with the Lewis structure. Look at the Lewis structure. It's nonpolar if both of these things are true. No lone pairs on the central atom, and all the atoms bonded to that central atom are the same, or they have the same electronegativity. That's kind of like the small print. If one of those is not true, if there's a lone pair in the central atom, or if you've got different atoms bonded to the central atom, it's a polar molecule. So let's practice that. Determine whether CH4 is polar. First thing is, we have to draw Lewis structure. Well, the carbon is going to have to be in the middle because hydrogen can only make one bond. So we've got hydrogens around it. We figure out how many valence electrons do we have. Well, the carbon has 4, each hydrogen has 4, so we have a total of 8 valence electrons. And the bonds, 2, 4, 6, 8, take up all 8 of those electrons. Carbon has an octet because it's got the 4 bonds. The hydrogens don't need octets, so very simple Lewis structure, but that's the Lewis structure for CH4. Once you've got that, ask yourself, are there no lone pairs on the central atom? Yes, there are no lone pairs on the central atom, right? There's no dots. Are these atoms that are bonded to the central atom the same? Yes. So both conditions are met. This is a nonpolar molecule. Any questions? Let's look at NH3. So again, with the hydrogens, you have a nitrogen. Oops. Let's try that again. Nitrogen. And the hydrogens will be bonded to it. And we count up electrons. Nitrogen has 5. The hydrogens bring 3. That's a total of 8. So we've got 2, 4, 6. We need a lone pair. There's 8. So there's our Lewis structure. And then we ask ourselves the two questions. Are there lone pairs in the central atom? There are lone pairs. So that first statement, no lone pairs in the central atom, is not true. We don't even have to go to the next step. This is a polar molecule. Polar molecules are asymmetrical. They don't have their charge evenly distributed. With this ammonia molecule, what we have is we have a trigonal pyramid shape. This is a lone pair up here, which is different than the others. So these polar bonds, nitrogen is more electronegative than hydrogen, and so these bonds all pull together here, and if we add those vectors, overall, there will be movement in that direction. The vector will be up. It's an unsymmetrical molecule. One end is different than the other, so it's polar. The nitrogen end, because nitrogen is more electronegative, this will be partially negative, and the hydrogens will be partially positive. Let's do SO2. You cannot just look at the formula. You have to look at the Lewis structure. So we'll probably want to put sulfur in the middle and oxygen on each side, and then there has to be at least a single bond there. And then each of these atoms has 6 valence electrons. So 3 times 6 is 18. We've got 18 electrons to mess around with here. So I already put in 2, 4, 6, 8, 10, 12, 14, 16, 18. What do we do when we run out of electrons? Make another bond. So we're going to have to make a multiple bond. So I'm going to take one of these lone pairs from the sulfur, and I'm going to share it with this oxygen because he's not getting enough. Now I check, and this oxygen has 2, 4, 6, 8. The sulfur has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Everybody's got an octet. Look at the Lewis structure. Is there a lone pair on the central atom? Yes. So is it polar or nonpolar? It's polar. See, that's not too hard, is it? If you see a lone pair on the central atom, bam, that's a polar molecule. Just want to do one more example. I should have done this on the previous one. What if we have something like this? I'll just draw the Lewis structure to speed things up. Polar or nonpolar? Polar. So the central atom has no lone pairs. These lone pairs don't matter at all. The central atom doesn't have any lone pairs. But are all the atoms bonded to it the same? No. This chlorine is more electronegative, and so it's going to hog the electrons. This molecule is not symmetrical, so this is going to be a polar molecule. Any questions? So now we can answer the question why oil and water don't mix. Water molecules are polar. Oil molecules are nonpolar. They are carbons and hydrogens. All of their bonds are nonpolar, and so the molecule itself is nonpolar. Polar molecules are attracted to each other a lot like magnets are. So there's a north pole and a south pole of a magnet. The south pole is attracted to the north pole of the next magnet. If you turn this around and try to stick those magnets together, you can't. It's very, very difficult because they're pushing each other apart. So this water molecule, this hydrogen has a partial positive charge. The oxygen has a partial negative charge. Opposites attract. And so the dipole moments of these molecules cause them to be attracted to each other. When you have nonpolar molecules, they don't have this attraction, these dipole moments. So their attraction is much weaker. So mixing oil and water is analogous to mixing magnetic marbles with regular glass marbles. Magnetic marbles are going to stick to each other, right? So you drop all of these marbles in a bucket, say, and shake them around, and what happens? You've probably never done this. I've never actually done this. I want to get my hands on some of these. As soon as I leave class, then I forget to go on Amazon and look for them, because I would love to have these to play with. The magnetic marbles, you can imagine, are going to clump together because they're attracted to each other. These glass marbles are not at all attracted to the magnetic marbles. They're not really attracted to each other either, right? They just roll around, right? Marbles don't stick together. So these are like the oil molecules or the nonpolar molecules. They're not attracted to each other. They're not especially attracted to the magnetic marbles. The magnetic marbles are like polar molecules. They're very attracted to each other. So they clump together and they tend to exclude the nonpolar ones. So that's what's happening here is polar molecules are clumping together and they're pushing out the oil or the nonpolar substance. Any questions? So you probably know from personal experience that grease and oil don't wash away with just water. If you're baking cookies or a cake or something where you have to grease the pan and you get Crisco all over your fingers, can you just go to the sink and rinse that off with running water? No, it just doesn't come off, right? If you had sticky sugar all over your fingers, that would just rinse right off, but grease doesn't. Grease doesn't mix with the water because of what we just talked about. So how do you get the grease off? You have to use soap. How does soap work? Ever think about that? So here's an illustration of a soap molecule. A soap molecule has this long nonpolar chain. It's carbon and hydrogen atoms, and so this part is very nonpolar. This end, though, has oxygens, and this end is polar. So this has a negative charge. This polar end attracts the water molecules. The nonpolar end mixes very well with the grease. The grease is, getting excluded from the water, but it can hang out here with this nonpolar tail, which is also getting excluded from the water. Now, I always have to draw this picture. One of these days, I'll put a decent one on here. So here we've got our grease glob. It's not a molecule. And what happens with the soap is the nonpolar tails will get into the soap. The nonpolar tails of the soap get into the grease. And what we have on the outside are those polar heads. Come on, marker. So these are the polar heads of the soap molecules. Sort of like circling the wagon. So out here, we've got, on the outside of this sphere, we've got these polar parts of the soap molecules. The polar part mixes very well with the water molecules. And so the soap can break the grease into small, very small globules and allow it to pass through with the water and get washed away. And that's how soap works. Any questions?